Okay, welcome viewers for today's tutorials. The tutorials has been sponsored by Proficient U Education Services. Education Services is an education consultancy that deals with, uh, I mean, high school, candidates in high school, career guidance, the pre-university, training, and also proficiency in language or language proficiency. So if you need to get more information about us, you need to contact us via the www.proficientu.com. So today we do tutorials in a lot of content, including other subjects. So today we shall deliver one in science, and this will be in practical in chemistry high school. So this will target the target group in this case are the candidate class in high school, that's the form 4. So behind me here is the wall that I'll be using to write that which whenever I'll be able to write. So about the practicals, this is the paper 3, and practicals, there are two main parts of practicals in chemistry. The first one is quantitative analysis, right here. Quantitative analysis. So quantitative analysis is about the titration. Is about titration, volumetric analysis. You can call it quantitative analysis or volumetric analysis. It is all about titration. And in titration, we normally have two solutions that are normally prepared. And in these two solutions, one of them is known, the other isn't known. So the second main part of practicals, we have qualitative analysis. Qualitative analysis. Now, in qualitative analysis, this involves the test of ions, both the cations, the anions, and also the gases. Now, but for today, we shall embark on the quantitative analysis. As I mentioned before, quantitative analysis is also referred to as volumetric analysis, and it is about titration. Now, so we shall deal with the titration. Now, in titration, as I said, there are normally two solutions. In this case, one of them is normally known. So we normally use two chemicals in aqueous state are normally used. Two chemicals in aqueous state are normally used. Now, one of these chemicals in aqueous state is normally of a known concentration. Its concentration is normally known. As you know that in any prepared solution, you normally have what makes a solution are normally either a solute and a solvent. So in this case, the amount of solute in a given solution normally determines the concentration, the ratio that is of the solute solvent in a given solution normally determines the solution formed. So in this case, One of the solutions that are used in titration is of non-concentration, as a non-concentration. The other one has a non-concentration. Now, using these two, there is a scientific term that we refer to non-concentration, a solution of non-concentration during titration. Now, in this case, that is normally called analyte. It's normally called titrant. Titrant. A solution of non-concentration is normally called titrant. Now, whereas the solution of a non-concentration is chemically known as titrant. So we have titrant and titrant. So if you're not familiar or you're not used to the term titrant to refer to a non-concentration, you can call it analyte. So we have titrant or analyte. Now we will be going by the term analyte so that we avoid confusion between titrant and titrant, since they confuse when they are pronounced. So in this case, when I talk about when I mention titrant, your mind should be ringing the non-concentration. The same way, when I mention the term analyte, should be knowing that I'm referring to the unknown concentration. So in this case, we shall be having we shall be, we shall have a case study, and we shall name, we shall identify or label both our titrant and our analyte. So moving forward, we need to know the objective or the purpose or the reason as to why there should be titration. Now, why should we titrate? Having known that two solutions of both known and unknown concentrations are used, the purpose or the reason as to why we titrate is to purposefully identify or to determine the unknown concentration, or rather the analyte. To be able to know or to identify or to determine the analyte. That's why we need to titrate. That's the reason. Now, moving forward, I want us now to, even as we do this, even as we titrate, I want us now to go through what we need to use, like the apparatus that are normally used during titration, because it is very important that a candidate or a learner of science acquaint him or herself with the important or the main uh, apparatus that are used in the lab. So apparatus required or used. So the first one we have a burette. The first apparatus is burette. Burette is one of the apparatus that are used to measure accurate volumes of solutions. Now, we have number two. So we have burette right here. Number two, in titration, we need or you must use a pipette. Number three, you need to use beakers. So these beakers, they must be they're they're beakers, because as you can I'll show you the beakers. They must be more than two. The first two beakers, one must be containing must be containing the analyte. The other must be containing the titrant, so that there must be other empty beakers that will be using maybe to drain, or maybe if you need to if you've used any other substance, then you don't need to pour it out. At least you need to empty it into a free, empty, dry beaker. So we need more than two. So we need beakers, that is, we need conical flasks, conical flasks, because we need, apart from these four, we need a clamp and stand, clamp and stand. You don't have a clamp and stand for my case. Before me here, I have a clamp and stand type of stand. So there you can also use retort stand, retort stand, retort stand, or you can even have, so that you can even have the round stand, either clamp and stand or the round stand. Those have one stand. Now, so these are some of the. Apart from this, allow me to talk about this pipette slightly, because pipette doesn't work on its own. Pipette comes with another apparatus that it works with jointly. So pipette comes with, so you need to have a pipette or an either pipette filler, pipette and pipette filler, pipette and pipette filler, pipette filler. So that you'll be using this to fill the pipette, or even there are two methods that we can use to fill the pipette, and that I'll explain in the procedure after this. So these are the main apparatus that which you need. Also, I was forgetting the other one. You need to have a piece of white tile. White tile. Can use white tile or a piece of paper. Piece of white paper. Not just any piece of paper, it must be white. The reason I've stated. Now, other than this, the last one, I suppose you need to have a card. You need to have card reader. Card reader. So begin with the first one. In the now procedure, at least to demonstrate that which needs to that which transpires during practical, during titration, I'll state the use, or how the burette is used, how it is, how it works. So beginning with this pipette in the procedure now, so it allow me to rub off that I write. Okay. Now about the procedure. In the procedure, about the most main apparatus here, that is the burette. Burette is an apparatus that is tubular in manner, as you can see, which is calibrated or marked. It's normally marked or calibrated, with the lowest mark on the topmost and the highest mark on the bottom, just slightly above the top. So the burette has a tap below it, that which regulates the amount of liquid substance inside the burette as it is drained during titration. Now, burette works together with the measurements of the markings of the calibrations of the burette are normally measured in either cubic centimeters or millimeters. As you know, that the value one cubic centimeter is equivalent to 1 ml. So this is the value that we'll be using, but in most cases we'll be using the cubic centimeter. Now, so burette works together with the round support and the clamp stand, as you can see. So, and even you need to first fix the burette. You need to mount and fix the burette on the clamp and stand of the stand that which you have. So even as you do so, you must ensure that number one, that it is firmly fixed, and that number two, you fixed it such that there is an allowance just below the tap, such that you can have adequate time, adequate space to titrate, because you will be using conical flask to titrate. So you need to have adequate space below the base of the stand and where the tap is. There must be adequate space that must be considered. Now we have a pipette. Number two, we have pipette, as you can see, it is also marked, but not marked as that of the burette. So a pipette, the maximum capacity of a pipette is always 25 cubic centimeters or 25 milliliters, while that of the burette is normally marked the maximum of 50 cubic centimeters. So you need to know that. Now, slightly above the marks in both the pipette and the burette, there's always a round mark that has got a brown mark, can be either brown, mostly either brown or blue, depending on the mark that is used to calibrate by either the burette or the pipette. That mark normally shows the maximum capacity of that particular apparatus, if it is burette or pipette. That's what you need to know. So which means that even as you fill any of them, you must fill them unto that mark. That mark is called meniscus. It's called meniscus. It is spelled this way, meniscus. Now, the pipette works with the pipette filler. Works with the pipette filler. The pipette filler. So, or you can suck. You can suck, because using the two solutions that you need to use during titration, that is the analyte and the titrant. The analyte, we need to use the analyte. The titrant needs to be used to fill the burette. So I want us to now to learn to see how do we fill, how do we use an analyte to fill the burette. So you should know that between the analyte and the titrant, you need to use the titrant to fill the burette, whereas the analyte is pipetted within the pipette. Then it has to be transferred in a conical flask that is used during titration. So we need to first fill the burette with the titrant. So how do we fill the burette using a titrant? We need to use an extra apparatus, that is a small conical flask as this. So you need to put it, as you can see. Then you pour off the titrant such that you can fill the billet. Don't have to fill it to brim, and you don't have to fill it to the meniscus, because that doesn't guarantee that the titrant up to the meniscus is enough for the reaction. So you feel it just slightly above the calibration, just like that. So that's how we fill our burette. So how do we about the use of the pipette? As I said, you have two ways in which you can use the pipette. Number one, you can fix the rubber tubing or the filler uh, out at the mouth of it this way, or you can suck. You can suck. You can suck the solution, the solution of the analyte. So in this case, I want us to give the identity. I want us to identify our two solutions. That which we used, the titan that we used to fill the burette with, I want us to identify it as BA20. BA20. Whereas, and the BA20 solution, which is our titrant, contains, in terms of the content, in terms of the concentrate of whatever it is used to prepare it, it contains sulfuric 6 acid, chemical written this way. So that's what is used to prepare our titrant. Now, I want us to identify or label our analyte as BA21. And BA21 is a salt that is not known, because the cation in it isn't known. It's given by letter X. So in this case, it is the type of salt it is a carbonate one. So we have a carbonate salt. So in this case, that forms a formula of X2CO3 in this manner. So this is our analyte. Now, so using the analyte that contains, or that is a soluble carbonate salt of X, we pipette it, we pipette it into the pipette, then we use it, we transfer it onto the conical flask. We pipette it this way and transfer it onto the conical flask this way. So now we've now had our two solutions in the right positions. One we've used to fill the bread, one is now in our conical flask. Now, after having transferred the analyte onto the conical flask, it is imperative that you use both hands, and you need to use all the senses that you have. And that, how do we now titrate? One hand, because a normal human being has got two hands, the left and the right one, and it all depends. One should be holding the conical flask that contains the analyte, whereas the other one should be holding the tap of the burette. As you do that, you will be squeezing, you will be pressing or squeezing the pipette at the pipette tap, such that you let the contents of the burette onto the conical flask. As you do so, you shake, or use the chemical term is swell. You'll be swelling. Swell is written this way. You'll be swelling the content of within the conical flask. you do so, as you do that, do not, where your eyes should be set is on the conical flask. The conical flask is normally transparent, so even as you look through, the walls, can be able to see if the color changes. As you do that, remember I told you that among the product that we use there, we were able to use a white paper or a white tile. So you need to put a white paper or a white tile below the conical flask. Ideally, to enable us comfortably and easily read, note when the color changes. The moment the end point is reached, then the color changes. But even before we do that, before we continue titrating, we need to ensure that in this type of titration, we normally use, an indicator. So the indicators that are normally used are normally four, as stated. We have litmus, we have bromothymol blue, we have methyl orange, and of course we have phenolphthalein. Now, as per the circular that I was applied with here in the procedure, we are told that we will always be directed in the procedure in chemistry. Like in this case, we've been directed that we use methyl orange as the indicator, not any other. And we've been warned not to use phenolphthalein as it has adverse error and effects. So in this case, we'll be using, after transferring the contents of the analyte into the conical flask, you need to add the drops of the directed, indicator, in this case, methyl orange. Methyl orange. So how do we add methyl orange? Don't just add it, don't just pour. So you need to use an apparatus called a dropper. So you need to drop, to add the drops of methyl orange and to the analyte dropwise. So basically, the standard drops are normally between 2 to 3. So you add between 2 to 3 drops. 2 to 3 drops means either you add a minimum of 2 drops or a maximum of 3 drops. So a drop is termed as a drop. A drop is termed as a drop, however small it may be. So don't feel that your drop is too small, but you add others maybe to make it a full drop. A drop is a drop, so you add either 2 or 3. That's what the range 2 to 3 drops mean. After doing that, that's when now you swirl or shake as you let the contents in the burette into the conical flask, and so you do so. Allow me to explain this, the origin of molarity, because I said before that molarity is coined or coined from concentration. So concentration can be expressed in two ways. Either in grams per given volume, or moles per given volume. That's what you need to know. So in this case, how do we therefore express molarity from concentration? You do that. Molarity can only be expressed in one way, not two ways as concentration, much as we can get it from concentration. So molarity of any solution can be expressed either in moles per liter, not even moles per given volume. So it is upon us to first, from the concentration, you get moles per given volume, then change it to moles per liter. Then from there, you can therefore write it once as a molarity using the unit of molarity. So in this case, we need to first, because you're given the mass, you need to get the volume that which is what is equivalent to this given 9.80 grams. of this Ba20. Now, from there, the procedure, we are told that we're able to find from the table there, we're able to find that because that it is just but the analyte, and we got it averagely because to get the average there, we were able to get 24.7, 24 plus 24.6 plus 24.6. When you divide by 3, you're getting there around 73.9. If you divide by 3, you'll get there around 24.633 recurring. That is if you use your calculator correctly. So in this case, rounding off this to the nearest one decimal place, you get 24.6 cubic centimeter. So remember, this is the volume of our titrant, that is of Ba20, which is acidic. So in this case, it is therefore possible to say that in this solution, the amount of solute, that is the mass, which is 9.80 of this solution, is dissolved in 24.6 cubic centimeters. So there is 2 marks. So very fast. In this case, find the formula mass. The formula mass of this analyte solution containing X-carbonate. In this case, we'll be having formula mass is same as the RFM, the relative formula mass, because this is a compound, this is an ionic compound. So we need to, for this, we need to get the mass that which we are given there. For the procedure, we are given the mass of it, which is 13.8 grams. So in this case, we need to equate this mass to the number of moles that which we got for that. So like I said, that the simpler way of getting this is simply, now that you are given mass, you just need to find the formula mass, in this case the RFM. Why RFM? Because the compound here in the Ba20 is an ionic compound, because it's able to break into ions forming it. Because this is an acid that when ionizes, it liberates ions. Hydrogen ions and of course anions. So in this case, it is an ionic compound. So we need to get its RFM. As well as RFM of ionic compounds, RMM of now let's now get the sum of individual atoms of different elements in this ionic compound. So in this case, we shall do it in this manner. So the RM of hydrogen is normally 1. There are 2 in this compound because of subscript 2. So that is 2. Sulfur as an RM of 32. Oxygen, 1 atom, has an RM of 16 times 4, because there are 4 in this compound. There are 4 atoms of sulfur, oxygen. So in this case, here we have 2 plus 32 plus 16 times 4, you get 64. Add 64 to 32, you get 96. 96 plus 2, you get 98. So you get 98. So 98 is the RFM, or the formula mass of this compound. Compound there. So in this case, how do we get, when given mass and the RFM, how do we get molarity? You simply divide mass by the RFM. That's how simple it is. So in this case, molarity is equal to mass divided by RFM. So the mass there is given to be 9.80 grams divided by RFM. So the RFM, in this case, normally get what we call the molar mass. And the molar mass, for us to give us easy time, we need to find the molar mass here. So that the molar mass is simply the mass in 1 mole of any substance. So we need to divide this 98 grams by 1 mole so that we get the molar mass. So that we'll divide 98 by 1 mole, we get the molar mass as 98 grams per mole. The unit of molar mass is grams stroke mol. You should not include letter E at the end there. So therefore, here should be dividing by, should be the molar mass, which is 98 grams per mole. When we divide this one, divide grams will cancel grams, so what remains will be mole. So therefore, when you use your calculator correctly, you divide 9.80, you divide it by 98, you get 0.1. Now, don't leave your answer as 0.1. Normally, you should always give your values after calculations. You give your values to 3 significant figures. So in this case, this value 0.1 is just only one significant figure, because since 0 isn't significant in this case, so therefore it means we need to add 2 zeros beside 1. So therefore we'll be having 0.100. Then the unit of molar mass is capital M, read as molar, not M, that we have 0.011 molar. So that's the molarity of solution BA20. Now, having known that, let's continue to number 2, or how about this? Question number 2 states calculate the molarity of solution, don't get scared, BA21. Remember, it is just a solution of our X carbonate that we talked about, which is barely our analyte. So getting that will give you 4 marks. So in this case, I'll take the step that which you need to go through to move to need to get the 4 marks. Because 4 marks is just not just that easy to get. So getting the molarity of this solution BA21 of this, and because it formed our unknown concentration, unknown solution, that is. Now, so getting the molarity of this, it means we need to compare this. We need to write the chemical equation that took place whenever we reacted. Whenever we were titrating, we found that these substances combined, and therefore they reacted. So allow me to go through that chemical equation very fast. Then from there, from the stoichiometry of reaction, we find that this X carbonate, which is in solution form, reacted with the sulfuric acid. So in this manner. So for this reactants to form products, they must be able to dissociate into ions forming them. So in this case, this 2 is for the soft ion from this. So therefore, this will break into ions from it. That is X X ions and X positive ion, and therefore and the carbonate ion. This, like any other acid, this sulfuric acid will decompose to liberate hydrogen ions, and of course sulfate ions or radical. So in this case, what happens is that we find that the carbonate ion or radical is normally unstable ion that undergoes further decomposition to form carbonate. Carbonate has two atoms of oxygen but the common charges are the same, like the carbonate. So carbonate, since it is unstable ion, it further decomposes to carbonate and oxygen ion. Now, so what happens is that the formed carbonate ion will be oxidized to form carbon dioxide, whereas the formed oxygen ion alongside it will combine with hydrogen produced by the acid to form water in this manner. Hydrogen ions with oxygen valence ionic charge positive, valence 1, valence 2 there. When they are swapped to here, one you're going to have hydrogen substitute 2 return, oxygen substitute 1 of return, that you have water this way. Now, lastly, what happens is that the unreacted X ions and that of sulfate will combine to form a soluble sulfate salt. So, which will be in this manner. So, the valences will be solved in this manner to form the formula that is X2SO4. The state symbol is AQ, since it is a soluble sulfate salt. Now, because there's no way an acid and a soluble salt can form an insoluble. That is known from the topic salts. Okay, so like I said, others are the carbon dioxide and water in this manner. So this is the chemical equation showing the chemical reaction that took place during titration. Now, you will find that when you balance it, then you find that they balance, like X2 atoms, X2 atoms, carbon 1 balanced, oxygen 3 plus 4 on the right hand side, they are 7. This side 4 plus 2, 6 plus 1 balanced, they are 7. Now hydrogen 2, sulfur 1 this side. So therefore the equation is found to have balance in the ratio of 1 to 1. So the ratio that reactants react to form products is in the ratio of 1:1. 1:1. So extracting the stoichiometric equation or the stoichiometry of reaction. So you can extract stoichiometric equation from this. So the stoichiometric equation is that in this case, you will find that we break the compounds that are in aqueous state very fast, so that in this case, we'll be having this. Allow me to rub off this one first. We break the ones in aqueous state only, leaving alone those in either solid, liquid, or gaseous state unbroken. So that therefore we'll be having X. If the two atoms here, therefore, that will be the molecules in this case. So that this reacting with this one plus hydrogen this 2 is for this. Break this because it is in aqueous state. 2 molecules of X ion reacting with the sulfate ion. These remain unbroken. So this is so from this point you need to identify what we call the spectator ions. Spectator ions. Spectator ions are ions that have got similar or the same ionic charges. And number two, for ions to be spectator ions, number one, they must be having similar or the same ionic charges. Number two, they must be able to be in aqueous state. So, and number three, the atoms or in the ions must be of the same element. So in this case, the same elements or the same molecules. So in this case, we find that those which qualify those are this one. Okay, for number three, finding the formula mass of X carbonate. Formula mass also means is same as the RFM, which is the relative formula mass, since X carbonate is an ionic compound. So in this case, how do we find the RFM in this case? What we need to do here, we need to find the RFM of this, or the formula mass, they're the same. So we need to find the relative, the mass that is equal to 1 mole of this particular compound here. So we'll be using the moles of that which we got for the X carbonate. So in this case, we're able to find that the moles which is equal to this is 0.0984 moles, and this one is dissolved in the volume that which was used during titration for the analyte, which was the solution B2 BA21, so which we used 25 cubic centimeters. So it therefore means that when you use the comparison, you can say that if 0.0984 moles of 0.0984 mole of X carbonate is equal to 25.0 cubic centimeters. And this one, remember, it should also be equal to the mass of that particular, because from the procedure there, you're given the mass of that particular solute in this solution BA21 as 13.8. So you can take the moles, you equate to the mass here, so that we have that if 0.0984 mole of X carbonate is equal to 13.8 grams. So what about 1 mole? What about 1 mole? What about 1 mole of the same substance? What mass will it give us? Remember, the mass that 1 mole of any substance gives is, if that substance is an ionic compound, like in this case, then it is the RFM. If it is a molecular compound, it will give the relative molecular mass. If it is an element, it gives the relative atomic mass. So in this case, we multiply here, you have 1 mole multiplied by 13.8 grams, you divide by 0.0984 mole. So in this case, you cancel common units, moles cancel with moles. So what remains must be present, must be included in the answer we get. So when you use your calculator correctly, you divide 13.8 by 0.0984, we are getting 140 0.843924. So remember that this either relative RFM, RMM, or RAM should be written in whole number. So when you run off 140.843924 to the nearest whole number, shall be getting 141. So this 141 grams. So 141 grams is the relative formula mass, or the formula mass of this X carbonate. So that's how we get that. So since it contains 2 marks, this is how 2 marks are awarded. The first mark of the 2 you get when you compare, when you are able to identify the number of moles that is equal to the mass of the analyte, that is the which contains the X carbonate in this case. So this will give the first mark there. When you proceed and find the answer here, rounding it off to the nearest, whole number, so that you get 141. You get another mark there. So that's how you go about it. So let's finish up by doing the last question. That's question 4. Question 4. Allow me to rub off this one. Now, the last question in Roman 4, and it states, calculate the relative atomic mass of X. This carries 2 marks. Calculate the relative atomic mass. The abbreviation of relative atomic mass is what I mentioned in question Roman 3. That is the RAM. R for relative, A for atomic, and M for mass. So the relative atomic mass of X alone. But remember, X is an atom of a metallic element in the compound X carbonate. So solution under this. So how should we go about finding the relative atomic mass of this X in this X carbonate this way? So in this case, for us to be able to find the RAM of X alone, we need to use the formula for finding the relative formula mass. So the RFM that we got in question 1-3, will be equating it on how we need to find it. Remember, the RFM, or the the formula mass of X carbonate, which we got to be 141, is simply the sum of the relative atomic masses of the individual elements in this compound X carbonate. So in this case, how is it achieved? By adding them. So we shall add them here, then equate to 141, because it is our relative formula mass, or the formula mass. So in this case will be, since X isn't known, let's write it, and it is a letter that represents the chemical symbol of that element there. So take it as it is. So it has got 2 atoms. 2 here, written as a subscript, shows the number of atoms of that particular element in this compound. So we have 2 X. You multiply by 2 because there are 2 atoms. So we have X times 2, or 2 times X, whichever comes first. So the product remains the same. I'm using dot here to represent multiplication sign, since we're using X to avoid confusion. X by X, to avoid the sign and the atom, or the chemical element. Now, so we have this. We add to the second element is carbon. Carbon has an RAM of 12. You add to that RAM of oxygen, which is one atom of carbon. Oxygen has an RAM of 16. But there are 3 in this compound. So you have to multiply by 3 there to get the total mass of oxygen in this compound. So here, this you need to equate to 141. This is the RFM. This is how you get the RFM. Add this one. So multiply x by 2, you get 2x. Add to 12. You multiply 16 times 3, you get 48. You equate to 141. Now you add these like terms so that you have 2x plus 12 plus 48, you get 60. You equate to 141. So these ones are known. So you bring this 60 this side, so that since it is positive, it will be subtracted on this other side. So that you have 2x is equal to 141 minus 60. When you take away 60 from 141, you get 81. So that you have 2x is equal to 81. You need to find x alone. How do you find x when you have 2x is equal to 81? You need to divide through by the coefficient of x, which is 2. You divide through here by 2 so that you make the coefficient of x here 1. You'll be having x is equal to 40.5. So 40.5 is our relative atomic mass of x, and that is our answer. So it again has 2 marks. So the first mark you get when you equate, how do you find the RFM or the formula mass of that compound, that which contains x, is 141, this way. So this one, that will give you the first mark. So chemistry ends there. So what is left now, past this, is just simple arithmetics. So when you do the simple arithmetics, then you get the value of x, you get the remaining mark, that we have another 2 there. So this is the end. This is our last question for this. The others, as I said, are simple. So let us carry on and maybe look at how others can be calculated in our next video.